Hi there, my name's L19. I'm a professor of electrical and computer engineering at Georgia Tech. So far, we've looked at voltage-controlled amplifiers and voltage-controlled oscillators and all sorts of memoryless nonlinearities to shape waves in various ways. Now we will begin our discussion of voltage-controlled filters, and we'll be talking about nothing but voltage-controlled filters for the rest of the class. While there are some subtle differences between the sounds of VCAs and VCOs in various synthesizers, for instance, the Mini-Moog has some interesting aspects to its VCA circuitry. It's the voltage-controlled filters that pretty much give a particular synthesizer its unique sonic signature. In this lecture, we'll construct one-pole voltage-controlled filters based on operational transconductance amplifiers. Now, just as was the case with voltage-controlled amplifiers and voltage-controlled oscillators, in this lecture and the next few lectures, I'm mostly going to show you current-controlled filters, and it will be up to you to put a voltage-current conversion circuit of some sort in front of it. For filters, we'll typically use exponential converters like we looked at last time, although you may or may not bother with the cost of using a Timco resistor. I'm going to present two interpretations of these OTA-based filters. The first gets down and dirty with the nitty-gritty of the circuit aspects of the implementation, whereas the second is from a higher-level mathematical viewpoint of feedback system theory. Let us begin with the humble RC filter. Now we have a half-power cutoff point of 1 over RC in terms of radians per second. Of course, musicians don't like thinking in terms of radians per second, so we divide by 2 pi to get this half-power cutoff point in hertz. Now, let's play a game. One way to think about what the resistor is doing is it takes a look at the difference of the voltages at its terminals, and it produces a current according to that difference. Now, physically, that's kind of an odd way to think about it, but mathematically, that's the sort of equation you write down with Ohm's law. Well, let's think about what an OTA does. An OTA takes a look at the voltages at its inputs, and it produces a current according to the difference of those voltages. We characterize resistors in terms of their resistance, but we could also characterize resistors in terms of their conductance, 1 over their resistance. And, well, we already characterize OTAs in terms of GM, their transconductance. Now, in all of the schematics I'm going to show you in this lecture, I'm drawing the current control pin here, but I'm not going to bother drawing the rest of the current control generation circuitry. It's some sort of voltage to current converter, usually either linear or exponential in its characteristic, usually exponential for a VCA. As is our usual convention, I'm assuming that we're measuring this output voltage with some high impedance device, so no current is flowing into whatever we're measuring the output with. So whatever current is coming out of the resistor here is going into the capacitor, and whatever current here is being dumped out of the OTA is going into the capacitor. And, well, what is the relationship here? I'll have Vn minus Vout divided by R will give me the current flowing through the resistor. And, well, I'll have V plus minus V minus at the inputs of the OTA multiplied by the transconductance of the OTA flowing out of the OTA. And what is the voltage here at the negative terminal? Well, it's Vout. So essentially what I've done is I've replaced the resistor with an OTA. So I've built a one-pole low-pass filter here, and to find out what the half-power cutoff point is, all I need to do is replace 1 over R in the formula with the transconductance gain. So instead of a cutoff of 1 over RC in radians per second, I have a cutoff of GM over C in radians per second, and of course we divide that 2 pi to get it into hertz. And what is the gain of the OTA? Well, that's approximately 19.2 times IABC, which is the current flowing into the control pin input. So, as I increase the current flowing into the control pin, I increase the cutoff frequency of the filter, and as I decrease that current, I'll decrease the cutoff frequency of the filter. Of course, we might be feeding something that doesn't have an infinite input impedance, so something we might do here is to place a buffer at the output And this triangle is basically an ideal voltage buffer. This is the sort of thing you can build with an op-amp by putting the input into the positive terminal and taking the negative terminal and connecting that to the output. Or you could use something like a emitter follower if you're using a BJT, or a source follower if you're using a JFET. Here we're just assuming it's an ideal voltage buffer. Now, when OTAs are used as part of an integrated circuit design, I see things like this quite often. But every time I've seen people build filters on a PCB where the most integrated element is an OTA chip like a CA3080 or an LM13700, I always see them take the feedback voltage from after this buffer. One thing that I have thought of is that something like the LM13700 doesn't have infinite input impedances. There is a bit of a current flowing through here, so maybe taking the output from the buffer here is a good idea, so you don't wind up stealing current that should be going through the cap that winds up flowing into the negative terminal when we don't want it to. And I would like to invite folks more knowledgeable about this topic than I am to comment about why we would want to take the feedback from the output of the buffer instead of directly from the capacitor. Now, these two circuits aren't entirely equivalent. There's a big difference in terms of what's happening on the VN side. With the OTA circuit, VN is presented with a high input impedance, whereas with the RC circuit, whatever source is providing VN sees an input impedance of this resistor plus the impedance of the capacitor. We usually assume that VN is being provided by an ideal voltage source, and if we make that assumption, then these two circuits would be essentially equivalent. But of course, if this is not an ideal voltage source, then these would be doing different things. And this issue comes up when we look at using this kind of OTA replacing resistors trick on cell and key filters. So we'll look at the consequences of that in a later lecture. Another problem that we should consider is that OTAs are only linear, i.e. they only give you this nice clear transconductance characteristic over a fairly limited range of voltages, somewhere around the plus minus 10 millivolt kind of range. Whereas the resistor can handle a wide range of voltages before it starts to go nonlinear in some weird, freaky way. And if it's starting to go nonlinear, it's probably also starting to get hot and exploding and doing stuff like that too. So one way to keep this nice linear framework is to place some of these resistor dividers in front of the OTA inputs like we did in the VCA lecture. Here I'm assuming that the R bigs are the same and that the R smalls are the same. You don't have to. If you wanted to set these to be different for some reason, you could go ahead and write down the equations for the circuit and solve them. But if you keep them sensible the way I've drawn here, what you could do is you could take the effect of the attenuation of this ladder and just fold it into the gain of the OTA. So what is the total transconductance gain, including this resistive divider? Well, I would have R small over R small plus R big. That's just the standard resistor divider formula, times that transconductance. So this is like the transconductance gain of the whole thing, including those resistors. And of course, it's often convenient to approximate R big plus R small as being R big, and we have this nice convenient formula. Now you could build an inverting version of this filter by plugging the input into the negative terminal instead of into the positive terminal, in which case we just ground the positive terminal. Now the figure in the lower right here is not exactly an inverting version of the figure in the upper left. In the version of the upper left, the feedback loop and the input have separate R small resistors. The way we've drawn it here, the feedback loop and the input wind up sharing an R small resistor. So the analysis on this, if you wanted to do it from scratch, would be a little bit more complicated. You could use superposition on it. The main difference here is that now, looking from the point of view of the output voltage here that's being fed back, the resistance you would be dividing over using the idea of superposition. If you ground VN here temporarily, well, that's not R small anymore. It's R small in parallel with R big. Similarly, if you use a superposition argument and think about what is happening from VN's point of view, if we temporarily ground the V outside, again, the lower rung of that divider is not R small. It's going to be R small in parallel with R big. But usually we just go ahead and use this formula anyway. We just have to realize that to get to that point, we would also have to approximate having a big resistance in parallel with a small resistance as just being that small resistance. Once we've made that approximation, then we can get to this kind of formula and eventually this formula here. And if you wanted a more precise formula, you can go sit down and work all that out. So far, I've presented an interpretation of these filters that's highly tied to a circuit's viewpoint. We took resistors and replaced them with OTA-Cs. We can also consider these circuits from a higher level mathematical viewpoint in terms of feedback systems. So stepping away from the specifics of voltages and currents, let's just imagine we have a generic input X, a function of time, and a generic output Y. And we have a system function, aka a transfer function in the middle here, which I'm specifying in the Laplace domain, the S domain, using a capital letter H. And the OL here stands for open loop. Now in this class, we don't really need a lot of Laplace transform theory. There's no need for partial fraction expansions or taking inverse Laplace transforms. And ultimately, you can think of S as just a placeholder that we're eventually going to substitute j omega in order to get a frequency response. Anyway, here we have some negative feedback as indicated by this minus sign, and the amount of feedback is controlled by this k. The triangle here just represents a gain of k. So the Laplace transform of the output of the system corresponds to the Laplace transform of the input times the transfer function. And this is the transfer function in the sense of the Laplace transform of an impulse response of a linear time invariant system. This isn't a transfer function in the sense of a instantaneous input-output relationship of a memoryless nonlinearity like we looked at in all of the wave shaping lectures. I'm using the term transfer function in a different way here. These are also called system functions. Anyway, what's the input? Well, I have this big X of S, which is the Laplace transform of the input, minus k times the Laplace transform of the output that's being fed back. If I take this open loop transfer function and distribute it through the expression, I can then move all of the terms that have y in them to the left-hand side. And then if I factor out ys, I get this expression here. I have y on the left side, x on the right side. And then I can take both sides, divide by x, and then also take both sides and divide by this 1 plus k big HOLS here. And then I wind up with this sort of formula. And this y over x, I can think of as a new transfer function of the closed loop system. CL stands for closed loop. And I can take this entire feedback configuration and replace it with a simple new system given by this particular formula. So notice the open loop transfer function appears in both the numerator and the denominator, but the feedback gain here only shows up in the denominator. So that's a general formula. Specifically, let's imagine that our open loop system is just an integrator with gain omega c. So dividing by s in the Laplace domain corresponds to integration in the time domain. Also, let's just let k equal 1. If I do that, I can plug in the specific open loop transfer function in my feedback formula and wind up with omega c over s over 1 plus k omega c over s. And I've let k equal 1, so the k goes away. And then I can take the numerator and the denominator and multiply them both by s to clear out the fraction there. And I'm left with omega c over s plus omega c. And conveniently, this is the transfer function of a first-order low-pass filter with a half-power cutoff point of omega c, which justifies me calling this omega c to begin with. If I wanted to be more careful in this derivation, I could have called it something like Fred, and then at the end we would see that Fred indeed deserves the title omega c. Okay, so that was very mathy. How would you implement this with a circuit? Well, maybe you would be representing these things in terms of voltages and currents. And oh, very conveniently, An OTA has a differential voltage input, so it has an input sitting here facilitating that negative feedback. And conveniently, what do capacitors like to do? Well, capacitors like to take information represented as currents, integrate them, divide them by C, and then spit out a voltage. And what does the OTA like to do? Well, the OTA likes to take the difference of voltages here and produce a current where it takes that difference and multiplies it by the transconductance gain. So what is omega C here? Well, omega C is the transconductance gain divided by the capacitance. And everything works out nicely. Now, we started with a fairly circuits-oriented derivation where we took an RC filter and replaced the resistance with an OTA. If we take this higher-level viewpoint, we can then apply the same kind of idea to build filters from other kinds of circuit components. For instance, circuits like the SSI2164 that take current inputs and produce current outputs. So what about high-pass filters? You can take a low-pass RC filter, swap the roles of the resistor and the capacitor, and you wind up with a high-pass filter with the same half-power cutoff point. Here, let me redraw this slightly and put the ground in the upper left of the schematic and the input in the lower right. Now we can do the same sort of trick of replacing the resistor with the OTA. Here, the positive terminal is grounded, and the output comes to the negative terminal, but now the same sort of idea works. Ideally, there's no current flowing into the negative input here, so whatever current flows out of the resistor and down into the cap, we can think about flowing out of the OTA and down through the cap. Or mathematically, we could equivalently think about a current flowing out of the voltage source providing the input here, and we could think about a similar current as flowing into the OTA. Remember, whether a current is positive or negative just depends on the way you've drawn your arrows. They're equivalent either way. And once we've made that OTA replacement, we've replaced 1 over RC with the transconductance gain, which in practice we've generally been writing as 19.2 times the input control current. This 19.2 is sort of a typical 77 degrees Fahrenheit, 25 degrees Celsius, 298 Kelvin. Some people commenting on the last lecture pointed out that Kelvin is just Kelvin, it's not degrees Kelvin. But as we saw in the last lecture, this can slide around a bit, but we generally make this kind of assumption when we're doing things like, say, figuring out what value of capacitor we want to use. Now, as with the low-pass filter, we could put a buffer here to help separate what's happening at this node with whatever might otherwise load the circuit down, and we can also take the output that's fed back to the OTA from the output of the buffer instead of directly from the output of the OTA. And to deal with the fact that OTAs are only linear over a limited input range, we could put our usual R small, R big divide down ladder here and make the same approximations we have before to get this nice formula for the cutoff. So let's take a look at some patents. Here's a patent from Dave Rossum, one of the founders of EMU Systems. And in this patent, he discusses using operational transconductance amplifiers to build low-pass filters. So we have our capacitors as we've seen before. Here he's explicitly using an operational amplifier to form the voltage buffer. He's using the same symbol for OTAs, but by the fact that you have the separate current input, you know it's an OTA, not a regular op-amp. Down here in Figure 7, he has the non-inverting configuration that we looked at. And up here in Figure 6, he has that inverting configuration that we looked at where the input is put into the negative terminal. So modulo these few approximations we made with the resistors, the output we get from this circuit is the same as the output we get from this circuit. It's just inverted. Further, in these set of figures in this patent, he starts to simplify things. He says things like, oh, well, what if this signal is already small? Then you don't need those voltage dividers. Oh, what if you can assume that you're feeding a high impedance circuit? Well, then you can get rid of the buffer. So the patent actually presents these circuits in the opposite order of what I presented them in just now. So in these circuits here, where the input is going through the capacitor, these are the high-pass filters. As an illustration of what the OTAs in this kind of circuit might be, Here he presents the basic 4-BJT OTA that we looked at in the Buchla 259 lecture. And as an example of an alternative to an op-amp for a buffer you might put on a circuit, he presents this combination of a JFET and a BJT, where the BJT is handy for its comparatively low output impedance, and the JFET is useful for its comparatively high input impedance. Although, if I remember correctly, in the SSM2040 filter chip that he designed, the whole thing's done with BJTs. Here's another patent, this one by the ARP company. Here, the transconductance symbol isn't a triangle, it's actually a square. So you can add the square to the library of OTA symbols that you've seen. And in this particular patent, they talk about setting A, D, and B here to different things in order to build different kinds of filters. One thing to notice about this particular configuration that's different is that instead of dumping the current down through a capacitor to ground, here the current is being fed into a capacitor in the feedback loop of an op-amp in an inverting configuration. So you can take all of the circuits that we've looked at in this lecture and reconfigure them to use this kind of style. Just as previously, we've seen some VCAs that dump the current out of the OTA through a resistor to ground. And then we've seen some VCAs that take the output of the OTA and feed them into a feedback loop of an op-amp. Now, throughout this entire lecture, we've been looking at one-pole filters. One-pole voltage-controlled filters are actually fairly rare. Usually you have filters that are 2 poles or 4 poles because one-pole filters aren't very interesting. Also, if you look at the question of low-pass versus high-pass filters, low-pass filters are much more common. If a synthesizer has voltage-controlled filters at all, it will always have a low-pass filter. It may or may not have a high-pass filter. Here, all of those rarities combine in the Jupiter 8, which was frequently used by Nick Rhodes, the keyboard player for Duran Duran. Here we have an example of a high-pass filter in the Jupiter 8 that is just a one-pole filter. So here we have the OTA. Here we have the divide-down ladder of 150K for R big and 470 ohms for R small. The 470 ohm resistor here is just dealing with non-ideal effects of this chip. And here, instead of using an op-amp as a buffer, they're just using a JFET as a source follower. So the 33K here isn't that big of a deal. You have the JFET through this resistor to the negative rail. Here we have the drain of the JFET hooked to the positive rail voltage. And all this does is provide a nice high impedance buffer to buffer the output of the OTA. And then the current control circuitry is generated elsewhere. So here we have a one-pole high-pass filter. This high-pass filter actually feeds a much more complicated filter that's a series of 4 one-pole low-pass filters using OTAs. This kind of configuration where you have 4 one-pole filters in series, along with a feedback loop around the entire thing, is fairly common in synthesizers. So we'll look at the mathematics of that particular structure next time.